in design is one I had heard from him. And he's an excellent explainer in economics. I think it comes naturally to him. That's what I can tell about him. So Raptoshi, let's have fun. So let's get on.
Okay, thank you very much, Joydeep and other organizers for inviting me to give a talk in this workshop. I have been associated with CMC till recently, so I have that connect still now. Now, the thing is that this Google Meet thing, I have never presented on this, so I'm gonna try, sharing my screen. Please let me know if you can view it, right? Is it visible?
Professor Chaudhary is here.
So is my screen visible to all of you?
Saptarshi, we can see your screen.
Yes.
Yes?
Yes.
Great.
Yes, we can see your screen.
Yeah, great. And the slides as well, right? Okay. So I have taken the liberty to change the title of my talk a bit. So it was only on choice theory and game theory. So I have changed it to recent advances in choice theory and strategic analysis. So, before getting into the talk, let me try to give a structure of the talk entirely. So, choice theory is very broad. It kind of forms the, base of any economic analysis. So any economic analysis would have some sort of decision making, right? So if you think of any economic environment and economic agents, an integral part of the analysis would be the decision making. Now, if you come to talk about market, then there would be buyers and sellers, right? So for the buyers, it has to be like what to buy, at what price to buy, whether to negotiate for it or not, right? All these things, these are all decision-making problems. For the sellers as well, right? So we can understand that, by choice theory, what we mean is basically probably entire fundamental economic principle, right? That how to make decisions. Policy angle is also dependent on, these fundamental principles of choice. So giving an overview of choice theory is probably not a great idea. That's what I thought, particularly when there is a time limit of an hour or so. Same goes for game theory. It's one of the most important application areas of game theory is economics. So it's so enriched, so rich, in fact, that it's very difficult to kind of pinpoint a particular area arbitrarily. So what I have kind of decided is that, let me pick two particular areas of research, one from choice theory, the other one is from game theory. And these areas are very much growing, and somewhere they have some connect with computation. Just because the center is on mathematical and computational economics, I thought that this connect is very important, right? And not only that, I have to say one thing is that, a perpetual complaint against choice theory and game theory has been that these are very esoteric stuff, right? So, it's just that, thank you very much. It's just that you develop very, rigorous mathematical theory, and what ultimately happens is that you can't really apply them in practical life, right? So that has been a complaint, and this has been addressed recently. At least there have been several attempts to address this, right? So that's why computational economics are very broadly, or rather, an intersection of computational economics and microeconomics has come up. So to start with, I would try to focus on one particular, very narrow although, but very important area of choice theory. And I'll try to present some results from the ongoing research. First of all, I'm not going to present any of my papers here at all. It's going to be something which is a group of economists, microtheorists, they have been constantly working on, especially in the US. And I'll give this list of references towards the end. I'm not going to mention that this result is due to this person or these people. I'll give a list towards the end of the talk. And I don't really mind if any of you, wants to ask me any questions, any clarificatory or even other questions during my talk. Please don't type in the question answer box. I can't read it now. Even towards the end of it, it will be very difficult. So my request is that if you want to ask me any questions, please do it, instantaneously. So Classical choice theory. Let me begin a bit with classical choice theory, right? So typically you have a topological space X, a set of alternatives to choose from. Please don't think that this is only, a consumer who is choosing from a basket of alternatives, right? It's not like that. As I just said, that any decision-making problem could be actually formed in this particular structure, right? So I should tell you that, even classical choice theory, when it started developing, they didn't really focus only on consumer behavior, right? It's all about choosing something, taking some action from a set of options, right? So we assume that there is a topological space X, which is basically the set of options that you are choosing from. And choices are typically made by an economic individual according to her preference relation, right? So I'm not bringing in any bounded rationality and all these concepts here at all. It's very classical in that way, right? So this economic agent wants to maximize her own satisfaction in some way. So wants to pick up the best bundle or alternative for her. And she's just, making a decision according to a preference relation, right? Now, a challenging thing has been that, what is this preference relation, right? Even when I'm going out to the market to, make a choice, or even as an investor, I'm making a decision, right? I'm trying to do the best for myself, right? That is the assumption here. Let's say that is the assumption here. But what is my preference relation, right? Preference relation typically depicts a kind of a ranking of all the options, right? Which kind of tells me that which is the best option for me, right? It's very difficult to kind of talk about this preference relation in general, that what is this preference relation? But, for an analyst, from an economic analyst's point of view, it's very important to understand what is this preference relation, right? If it can be really, really inferred, think about it, that it's not only about you who is making the decision making, or who is making the choice. Many other economic agents whose welfare depend on your action, they would also be very keen to understand what is your preference relation, right? If an online shopping company, a seller can get to know what is exactly your preference relation, what is exactly your taste, then nothing like it, right? Then they can actually curate a nice package for you to tempt you, so that you kind of end up buying something from them. So inference of this preference relation has been something which is very important. Let's take a quick look at where we are in terms of, inferring this preference relation, which is not at all observable, right? This is very typical of classical choice theory, that there is a choice function. Basically, idea of the choice function is that, give me a set of options to choose from, and I will choose some alternative, or maybe a few alternatives from it. So basically, it's a mapping, right? Sigma is typically, this is basically the set of all subsets, right? Basically, one subset of capital X can be presented to me, so there would be some options, and I just choose something. C is simply that mapping, right? So a choice function is generated by a preference relation, right? If this happens, this is very, very standard, that you try to maximize your preference relation. So a choice function will pick exactly those options which are maximizing your preference relation, right? So C of A would be those alternatives which are maximizing your preference relation, right? From the given set of options. So this is very simple. Now, for analytical convenience, we postulate a utility function, right? That we always assume that there is a utility function which is being maximized. Notice that this particular representation, that a choice function is generated by a preference relation, it is very easy to relate to. I have a taste or preference or a ranking of the options, and I'm going to choose according to that. Where is this utility function coming from? The idea is simple convenience, analytical convenience, right? Mathematical convenience. You love to work with a function, right? Not too much with this preference relation, which is basically a binary relation, right? So you bring in this utility function, you postulate, okay, I'm maximizing according to my preference relation, right? Meaning I'm maximizing according to some utility function, which is exactly representing my preference relation this way, that, one alternative X is better than Y if utility derived from X is higher than utility derived from Y. So basically, you can say that individual is choosing according to this squiggle star. Squiggle star is the preference relation, right? Which is equivalent to maximizing U. However, we don't really observe U. It's a purely theoretical concept. And I would like to point out that even, there is so much emphasis on utility maximization, while we kind of not only do research, but also teach, right? But very fundamental thing is that even Samuelson in his book mentioned that Maximizing utility means that the behavior is as if maximizing some utility, right? Just focus on maximization of utility, but remember, it's a kind of a hypothetical concept. It's as if you are maximizing some utility because your behavior impacts, your behavior is captured by the observable data. Your utility is not. It's unobservable, right? So what is the task? The task has been to characterize the data, what we observe, right? If you are a decision maker, then I see the data, how you are choosing, what you are choosing. Remember that choice function? I can kind of, look at some of the data points generated by that choice function. I give you some sets of options and you choose something. So those data points are actually can be observed, right? So task is, if there is a data, let's say, this kind of a data, that XK PK. XK is basically the bundle that you are choosing. XK is the alternative that you have chosen, right? And PK is the associated price vector. This is very simple to imagine this kind of a situation, right? Where, you just, this is very observable at different price levels. What are the different bundles that you are choosing, right? So at this particular price level, P1, I am choosing X1. In another environment, when the price vector becomes P2, I'm choosing X2. So I have this kind of a standard data set, right? Now I can say that, a utility function U would rationalize this data if this happens, that if Xk is the bundle that I'm choosing and Y I'm not choosing, but is affordable, Pk times Y is less than or equal to Pk.Xk, which means that Y is an alternative which I have discarded, right? Rather, I have chosen Xk. So it must be the case that utility derived from Y is less than utility that I could derive from Xk. That's why I'm choosing Xk, right? I could have chosen Y as well because Y is affordable. So you would rationalize this data if this happens. Now, idea is that give me a set of data, Xk Pk, right? Can I just look at this data, analyze it, and say that, hey, look, if this data has been generated by a decision maker, this decision maker is indeed a rational decision maker. In the sense, this decision maker is actually maximizing her preference relation or a utility function that represents it. It's not a very trivial question to put it. If you think about it, that I give you some data, some finite data, right? X1, P1, X2, P2, like this, till Xk, Pk at various price vectors. What are the bundles that you are choosing? And I'm asking you, analyze this data and no other information you have. Tell me whether the consumer who has produced this data is a rational consumer or not, in the sense that the consumer is maximizing according to some preference relation or not. It's one of the oldest theorems by Afriyat. This I had to mention here, although I'm not mentioning all the references, but this one I did mention because this is extremely critical theorem. This has kind of set the platform that this data can be rationalized if and only if it satisfies this condition called generalized axiom of revealed preference, right? Notice the question that I asked. I give you the data, Xk, Pk, and I have asked, has it been produced by a rational consumer? That means, is this, in a way I'm asking that, can you find out some condition which is being satisfied by this Xk, Pk, and which will ensure that, a preference relation is being maximized? I asked only this question, but this theorem is giving you both the answers, because this condition, GARP, this is not only necessary, but this is not only sufficient, this is also necessary, which means any data which is rationalizable, which can be actually obtained only by maximization of some utility function or preference relation, must satisfy this condition, right? This kind of forms the premise of classical choice theory. So what is this GARP? It's very easy to understand. It simply says that, when you have a sequence of such kind of a data, X1, P1, X2, P2 till Xk, Pk, and the situation is something like this, that Xk plus 1 times Pk is less than or equal to Xk, Pk for all small k from 1 to k minus 1, which simply means in the sequence, if you just look at this X1, X2, X3 till Xk, what is happening is that X2, for instance, X2 is very much affordable when the price situation is P1, right? But you are discarding it, and what you are doing, you are choosing X1, right? X2 times P1 is less than or equal to X1 P1, which means that X2 you could have purchased, but you didn't really purchase, right? You went to purchase X1. Similarly, X2 and X3 is affordable when it is price is P2, but you are actually choosing X2. So what is happening is that in this particular sequence from small k running from 1 to capital K, every subsequent bundle, right, is basically dominated by the former bundle in a revealed preference way. So what I can simply say is that through this sequence, every alternative xk is revealed to be preferred to xk plus 1, right? If so, if this happens from xk, x1, p1 till xk, pk, it mustn't be the case that this revealed preference relation is reversed when you are considering x1 and xk, right? So you start with x1 is revealed to be preferred to x2 is revealed to be preferred to x3, this goes on, x capital K minus 1 is also revealed to be preferred to x capital K. Now you are comparing between x1 and xk, then it cannot be the case that this relation is reversed. That means x capital K is revealed to be preferred to x1. This is not really possible, right? This is the condition. This is the GARP, right? If you know about transitive closure, it's some sort of a binary relation of that sort, right? Afria's theorem is very powerful. You know why? Because it's testable, right? Give me this data, I can easily test it, right? And not only it's testable, it's necessary and sufficient as well. If the data has been generated by a person who is maximizing utility, this condition must be satisfied. You can't get rid of it, right? It's that powerful. But the problem is identification, right? It still remains to be solved, by the way. So, what Afria's theorem would tell you is that it exists. If the data satisfies GARP, yes, preference is being maximized, right, on the back of it, right? Even when I am going out, I'm making some decisions and I'm producing some data, you are telling me that, yes, your data is satisfying, GARP. So you are indeed a preference relation maximizer. I would ask that, what is my preference relation? Please identify it, right? So let us focus on this identification part from the choice data. Some practical issues, the very first thing is that data could be large. These days, it's not very difficult to gather data, but it's often finite, right? Do you really deal with, infinite data very much for as far as choice behavior is concerned? It's very difficult. It can be very large, right? But it's often finite. At least, let's take an attempt. Let's give it a shot to solve for finite case, right? I know that, if you can assume that the data is infinite, it gives you a lot of strength. And probably it's not that difficult to identify the preference, theoretically at least, right? But let me ask this question. Is it possible to learn the entire preference relation with a large but finite data set? The question is not very trivial, by the way. That's why I have put entire preference in a boldface, right? Again, I am giving you a finite data set, maybe large but finite, right? And I'm asking whether the entire preference can be learned, can be found out. Right. So basically, I might give you the data about, n number of bundles, right? But I'm asking you that, capital N number of bundles are available. So give me your entire preference relation, right? Where capital N is much, much larger than small n, right? I'm giving you a sample and I'm asking you to kind of give me the information about the universal set. It's something like this. So it's not trivial. Let's call.
Sorry, can I just ask a quick question?
Yeah, sure.
I'm sorry if this is a silly question, but I just want to understand what you meant by preference relation. I mean, because we are now have prices as well. So do you mean for every price point?
So preference relation over the bundles, I already said a topological space of, options or alternatives from where the decision maker is choosing from, right? So the preference relation is defined over this set of options, right? So the prices, there is no preference relation over prices. Just, we are just interested to understand that how the decision maker is ranking across various options which are available to choose from, right? Prices definitely are coming in the environment. They're giving me some information, but we are interested in understanding that what is your preference ranking, let's say, of all the options which you can choose from. That's the idea. So entire preference relation is on that X, capital X, right?
Got it. Okay. Thanks.
Right. So consider a choice experiment. So I'm going to set up a simple, very simple environment with minimum possible number of assumptions, right? Which if we can solve or at least give some insights, that will be wonderful, right? Without assuming a lot of things in the environment. So suppose, think of, I'm using the word subject, meaning the decision maker, basically, right? It's an experiment, right? This individual or the decision maker is asked to choose an alternative from a very simple set, a binary set, xk and yk. K subscript I'm using because it's a time index, right? So this individual is being asked to choose an alternative from X1 and Y1, then again from X2 and Y2, then again X3 and Y2 like this, right? So you understand that it's kind of generating the sets, right? B1, B2 till BK. It's a finite experiment. Remember, we are within a finite environment. So it's a finite data set, right? So B1 is the first binary set, B2 is the second binary set like this. Even till end, you are asking him to or her to choose only from a binary set, right? And this sequence is finite, correct? The subject's choice of alternative from every pair is observed, right? A small piece of notation, sigma n, sigma subscript n is the collection of these binary sets, B1 through Bn. So as you can understand, this set of growing experiments will be like sigma 1, sigma 2 like this, right? So basically sigma small n is a subset of sigma small n plus 1, right? Because the experiment is growing. In every time period, you are asking the decision maker to choose from a new set, new binary set, right? And you are adding it to the experiment. But you stop in a finite way, right? Of course, you stop in a finite way. This is the setup. This is a very simple setup. The decision maker is never asked to choose from a set which contains more than 2 alternatives, right? So think about this model from the perspective of actually carrying it out in a laboratory. It's not that difficult, right? But it's a very clever setup. I will point out why that this binary thing matters, right? The moment you make it ternary or something, it might not really work, right? Maybe you kind of can already gauge that what it might be. Think about a binary relation, right? Now, what's the new thing about it, right? The new thing is this, that you have the preference environment, X and rho, or this capital P, right? X is the space of alternatives, and P is the capital P is the set of preference relations, right? Possible preference relations. C is the choice behavior, which is encoding the choice behavior, and sigma n is the sequence of experiments. You can easily say that a preference relation would rationalize the data, right? So you have a data. Your data is those binary sets, and what are the choices, right? In a finite experiment, right? X1, Y1, I'm choosing X1, X2, Y2, I'm choosing Y2, like this. Till Xk, Yk, I'm choosing something. This data is there. Now, a preference relation will rationalize this data, of course, if this happens, right? That the chosen alternative from XY would be at least as good as X as well as Y, at least as good. So even if you see XY is X, it's okay, right? So this is very easy to understand. Question is, you have to estimate this preference from this finite data set, and you have to estimate the preference relation over the entire data set, right? And you have to really unify the framework of revealed preference with econometrics, right? So
I want to ask you a question here.
Yeah, please.
Sigma n, you had this, what is this xy from sigma n? So these are any particular time, right? Not
Yes.
Just at any time. It could be any
Anytime.
of the sets, B1, B2, anything.
Yes, absolutely. You are just adding more binary sets, right?
No.
Time
I'm
period.
telling is XY is so every set is just having 2 elements.
Absolutely. Every set has 2 elements, right? And sigma contains all these binary sets, right? At any point of time.
Right.
Till that time, right? Okay. So the difficulty is this, that I have given you a finite data point, right, which is still only BK. So you have a union of BK, B1 till BK, right? All the binaries, but you have only this finite experiment. So you have the entire set of capital B, right, which is the union of all these BK, right? At best, you can infer the preference on this particular set capital B, right? Because you have only the data points on B, right? How can you actually infer the preference on the entire set of alternatives, right? So, if the subject's preference, for instance, behaves totally differently outside B, it's not really possible to have an approximation over the entire set X, right? So this immediately tells you that what is the condition that you need to impose in your model, right? Very, very natural 2 conditions. The first one is that your preference has to be continuous. You cannot really hope to, approximate the preference relation if it is discontinuous, right? Like lexicographic preference, right? And second, your B, the data set has to be dense in X, right? In an informal way, loosely speaking, observations should be sufficiently spread out, right? So these 2 conditions you need for sure. You cannot have discontinuity. You cannot have the set being non-dense in X, right? But these 2 conditions are not sufficient for a finite data set, right? What else do we need? we need to put some more structure or the conditions. And what I'm going to tell you is actually, trust me, this is the crux of the entire work that has been done so far, that how you actually, condition the environment, the space of preferences and the space of alternatives, right? First thing is you endow the space of preferences with closed convergence topology. It's a very simple topological concept, right? The idea is very simple. Remember, this is a space of preferences over the set of over the alternatives, right? Idea is very simple, that if you have two different individuals with similar preferences, I'll not get into the technicalities, but similar meaning, the distance between these preferences is sufficiently small. If you have so, I am a person, you are another person, I have a preference, you have maybe a different preference, but suppose our preferences are very close by according to some metric, then we should choose in a similar way. Remember, I'm not saying that we should choose the same alternative, but there should be similarity in the choice behavior. Again, the similarity you are also defining in terms of some metric. As you understand, it's a topology. You can get into all these things, right? So this property is necessary to be able to learn the preference from the finite data, right? This is the first. Second, you make capital X locally compact, separable. Important thing is you have to make it metrizable, completely metrizable, right? So that means you must have, a metric space structure on this and one-to-one bijection on that, so that you get a metric. It's important, right? These two conditions, along with that, make rho a closed set of locally strict preferences. This is not a big assumption, by the way. Most of the choice theoretic models assume this, right? Strict preference, well, I think it can be still relaxed. It doesn't really matter because we are assuming that it's a choice function. That's why we are talking about strict. Relax it to a correspondence or something, you can weaken this assumption as well, right? And the last point is this sigma n, this growing set of experiments, right? You are adding B in every period, right? You are asking the decision maker to choose an alternative in every period, right? So the experiment is growing. It should be exhaustive growing set of experiments. Every pair of alternatives is compared, right? Just this is the kind of a structure or the condition on the environment. That let's put this condition on the environment.
Saptarshi, why can't we just, instead of taking topological space, just take a separable metric space?
You can do that, actually. It's a very rich structure. Remember, it's a good question.
Space, as they're called.
I can tell you one thing. So this particular decision environment is general enough to go beyond individual choice. It also includes, any kind of decision making. That's why, this topological, the richer structure of topology is just, it's just enriching the environment so that you can accommodate many applications. But you're right, you can work with that as well. It's that simple, right? So that's all.
One question. So one example of a metric between preferences could be k-many distance. But what would be an example of a metric between choice behavior?
You mean, choice behavior?
So you said the individuals with similar preferences should have similar choice behavior. So you said if two preferences are close with respect to some metric, their choice behavior should be same with respect to close with respect to some other metric. So what should that? Can you give me an example of that? What the second metric could be? So choice behavior is choosing between if we take the binary example or the experiment example. Given x1 and x2, someone chooses x1. Given x3, x4, someone chooses x3. So here, what would be similar to
no, but you are choosing from capital X, right, which is a universal set of alternatives, right? So assume that it's Rn, so you can choose any metric, right? If you
okay. In that sense,
yeah.
Right.
I have a question. This is Rupali. So
Yeah.
if we have binary relation, so if we have in the set of two alternatives, you're comparing over all alternatives, then we can generate the exact preference relation, right? So if I know that for the entire set of alternatives that I have, if the person has chosen on binary sets of all possible combinations, then we can generate the exact
no, but please understand that your data set is finite here.
Okay, so when you're saying that, so what does it mean when you're saying that your sigma n is an exhaustive growing set of experiments?
In the limit. It's not in the limit, right?
Okay.
Everything you are doing in the limit. right here, because whatever data set that you have, obviously remember that this is the assumption, or this is the structure on the entire environment, right? But the data set ultimately you get is a very finite data set. Let's say x1, y1, x2, y2, x3, y3, x4, y4. That's all, right? That's the experiment that you are generating, and that is the data point that you are getting. But the environment has this assumption behind, right? That's all.
Thanks.
Right? Yeah. In fact, this is the crux of the thing. Now you have the theorem immediately. Not immediately, I'm sorry. I shouldn't be saying immediately. It's a kind of recursive theorem. What is it saying? It's simply saying that C is an arbitrary choice function in this environment, as specified earlier. Now, suppose for every n, right, a preference squiggle n rationalizes the observed choice on sigma n. So remember that sigma 1, sigma 2, the experiment is growing, right? So suppose you have some sigma n, which contains n binary data sets, right? So x1, x2, x1, y1, x2, y2 till xn, yn. And suppose a preference relation, squiggle n rationalizes that observed choices on sigma n, right? And suppose for every n, you have such kind of a preference relation, right? For every n. Then the theorem says that there exists a preference squiggle star such that the limit of this squiggle k will be that squiggle star, right? So it simply says that if you can kind of construct the experiments, right, this kind of binary sets that you are generating and you are asking the person to choose, right? So for every such sigma n, you have some preference relation which is rationalizing this, right? So you're expanding the experiment set, right? And for every stage, you have some preference relation which is rationalizing that particular sigma n. And for every n, you have that. Then definitely the sequence of squiggle n, right? Squiggle n, squiggle 1 is rationalizing the very set sigma 1, squiggle 2 is rationalizing the very set sigma 2. Like this, you are expanding and you have a preference relation for every stage. And the limit of this sigma k, right, which you are generating, the sequence, suppose you find out a limit, right? This limit will actually be the squiggle star, which is indeed the preference relation, the underlying preference relation of the individual, right? It's as simple as that. So you look at the strength of the theorem. It's simply saying that the environment that you have established, in that environment, right, if it is the case that every stage you find out a preference relation, which is rationalizing that particular data, right, then you form that sequence. The limit of this particular sequence of squiggle k, which is squiggle star, that is indeed the the preference relation, underlying preference relation, and this is unique. It is an existence result. It simply says that yes, hey, look, if you kind of consider this kind of experiment, and if you can generate this kind of preference relation for every stage, and if you can take a limit of it, if limit exists, that will indeed be the underlying genuine preference relation, right? And it is unique. It's not even that there is no a multiplicity problem. It's a very strong result from the existence point of view. But again, we have to still talk about that, how to compute it, right? You can apply, by the way, this kind of also partially, it kind of answers Joydeep's question that, you can apply this to more specific settings. So for instance, the data set is X1, B1, where X1 is the chosen alternative and B1 is our very famous budget set, right? The very, the micro, the very first lecture, right? The budget set that we have, B1 and X1 is the choice. Like this, you can actually kind of take the sequence of data in that way as well, where BKs, these are all linear budgets, right? And under some kind of Lipschitz kind of a condition and the boundary condition, again, the sequence of preferences that rationalizes this observation, they converge to a unique preference relation. In fact, it's a very strong result as well. But remember, it was only for linear budgets, right? The environment that I just presented, that is very general, right? Very general. In fact, this holds good for nonlinear budget sets as well. That is presented in another paper. But the one that I just discussed is fairly general. It has nothing to do with budget set, linearity, nonlinearity, nothing, right? It's just the choice environment that I presented, right? Give me a choice set, tell me what to choose, tell me what is my choice. That's all, right? You don't have to go beyond that at all. Now, identification of the preference is the next challenge. I quickly come to statistical model. By the way, I should go till which time? I mean, 6:16 till when I have the time? If one of the organizers,
7, I think.
including the questions, right?
Yeah.
Okay. So I have around half an hour, let's say. Okay. So identification, we have to set up a statistical model, right? This part is interesting, and let's see how it goes, right? I would claim that this is a nice mixture of, micro theory as well as statistical significance models, right? So X, P, these we know what they are, is a set of alternatives. P is the set of all preference relations. Lambda is basically the probability measure according to which alternatives are drawn for the experiment. These binary sets are drawn according to this lambda probability measure, right? And Q is the error probability function. Basically, the individual is allowed to make mistakes. So basically, what you are doing, you are making the choice stochastic. It's no longer deterministic, right? So whenever you are getting into a statistical model, you are allowing the choice to be stochastic. So Q is the error probability function, right? That's the environment that you have, right? Now look, a simple estimator is proposed, right? You have to estimate the preference relation from a given set of data, right, which is finite, right? This is the estimator which is being proposed. What is it? Find a preference relation that minimizes the number of observations which are not really consistent with the preference, but it is minimized. So this is the idea. I have a set of data, choice data, and I propose a preference relation, right? This preference relation and the choice data may not really be consistent with each other. There will be some observations which are inconsistent with the preference that I am proposing. So how many such preferences could be there? Many, right? Find out the preference relation which is minimizing the number of observations which are inconsistent with the preference. Basically, you are minimizing the error, right? You can easily understand that this is basically the concept is you are minimizing the K-mean distance, right? That's the idea, right? And notice, I would like to point out one thing here. This approach is actually model free. You are not really assuming anything specific to this probability measure lambda or this distribution Q, right? It's kind of model free. It's anything, right? You don't have to assume anything specific, right? You are just following this estimator, which is based on the principle of K-mean distance minimization. That's all, right? You can easily estimate a preference relation from a given finite data, right? Right. This assumption is required, but this is more technical, that it says that lambda has full support on X. And, for those alternatives, for where, the preference relation is indifferent, it provides indifference between X and Y, lambda has to be 0. Again, you want to bring out the strict preference relation. That's why. Otherwise, this is not that crucial, right? But this is a kind of a variant of that third assumption of denseness in some way. Theorem. The theorem says that under these assumptions, if you have estimated this K-mean minimizing estimator for a given sample sigma n, right? Take the limit of this squiggle n, right? In probability, suppose it is limiting to squiggle star, then squiggle star indeed is the subject's preference, right? So basically, you have the sample, construct this K-mean, estimate this K-mean minimizing estimator preference relation, right? Find out the limit of this in probability. That will indeed be the genuine or underlying preference relation over the entire set of alternatives, which is the squiggle star. This is indeed a great result, right? You can actually estimate the underlying preference relation, right? So in fact, this is the main result of this entire area of research that I wanted to present today, right? So so I think it's a combination of fundamental choice theory as well as some nice statistical techniques which are not terribly tough, probably, at least for theoreticians like me and all, who are always very wary of econometric techniques. At least we can gather some courage to at least take a look at this kind of estimations, right? So, but beyond that kind of light statement, look at the strength of this result. I think it's very, very nice, right, in a way. So, these are the references. Afriat, obviously, Varian and Afriat. So, by the way, this is no way exhaustive list of references, but it will indicate something about the entire presentation that I just made. Afriat and Variance, these two papers, they form, this is more in line with the classical choice theory, right? Masculin's this paper, basically, this is all about that, when you have this choice data, finite choice data, but you have linear budgets, right? That is the paper by Masculin, published in JET, 1974. François Forges and Minelli, they have this JET paper in 2009, This is about nonlinear budget sets as well. So they apply this FEF, they start from FEF theorem, then they get into this finite choice data, and then they try to understand if there is a limiting behavior or not for nonlinear budget sets. But again, both these papers were regarding budget sets, right? But the paper that I just presented, this is more general, right? I must mention about this paper by Kubler and others, right? This is one of the very first papers on identification of preference relation from some sort of a demand model. Although they considered asset demand, but still, right? This is the very first step. And the main paper that I just kind of based my presentation on is this beautiful paper by Chambers, Eschnicke, and Lambert, which is either forthcoming in Econometrica or it's published already, recovering preferences from finite data. This is in fact, I have followed this paper only mostly, although I have touched through all this in some of the other way, right? So there I end with my first part of the presentation on choice theory. And just because I have some time and the title says that I have to talk a bit about the strategic interactions, let me get into mechanism design part a bit. But I'll be very quick on this part because there is not much time left. So,
before you begin, there is a question from Umang. If you can answer that.
I'm sorry, I couldn't hear properly. Come again, please.
Can you hear me now?
Yes, better. Yeah, tell me.
So Umang has asked a question in the chat. So Umang, if you can ask the question now.
Yeah, sure.
Yeah. So basically, for the last theorem that you presented, do you need any assumptions on Q? I mean, surely if it's too large, then you can't say much about.
You mean this result?
The
estimation result? Statistical.
Yes. Yeah.
So what is your question? Assumption on
Q? So the error probability.
Yes. You don't need to assume any specific property for Q. Q is just a probability function, a choice, stochastic choice function. That's all.
But if Q is, let's say, like larger than half, for example, then clearly.
Yeah. It has to be just a probability function. That's all.
Okay.
Yeah. It's fairly general. It's model free. It's model free. That's the thing, right? Okay. I know it's surprising, but yes, it is. Right.
Okay, thanks.
Yeah, so this part of the lecture is about mechanism design and third-party information in mechanism design. Again, it somewhat it connects choice theory with mechanism design. So I start with the very, very well-researched problem about monopolists' optimal pricing mechanism for a buyer. The buyer has a private valuation for the good, right? Only the buyer knows it, right? And the buyer's value is drawn from some commonly known distribution, which is known to the seller. And we know Meyerson's, contribution about it, that what is the optimal mechanism that kind of extracts the maximum surplus, right? We know about this model, Meyerson 1981. It's kind of path breaking, right? The thing is, this stream of literature, it started on this premise that, this information asymmetry, that yes, I am the buyer and I know how much I value this product and I only know it. You are the mechanism designer or the seller. You don't really know it. You have an idea about it. You have the probability distribution, and you can actually design this optimal mechanism to extract the maximum surplus. Okay, there is information asymmetry, and this is the very classic mechanism design. But in real life, it's rather this kind of information asymmetry and the information flow is complicated. It's not that simple, right? A straightforward application of Meyerson's technique, if you want to do, then you have to assume away a lot of things, right? You have to abstract away from a lot of practicalities, right? You want to be very straight-jacketed that, okay, I want to apply Meyerson's technique, so let me assume away all the other problems. To give you an example, there have been many generalizations of Meyerson's model. I give you an example, right? So suppose the item for sale is endowed with a type. The idea is that, the item which is being sold by the seller, it has some type, and the buyer is not sure which type this product is, right? So buyer knows that if this is type 1, then this is the value, which I know. If this is type 2, then this is the value. But which type is this product, right? I don't really know, right? And suppose this realized value of the product is only known to the seller. Seller knows it, right? This is definitely a departure from Meyerson's standard model, right? Because although I know that, yes, this is the value for the product, I value the product this way, but that would be the case only if I know that this product is of this type. If there is a possibility that this product could be of another type, then I would know the value for that type, but I don't know which type the product is, right? So suppose this information is available with the seller. It's a kind of a structure, right? And there are many papers based on this structure, right? Seller has a leeway. Seller has this information that which type this product is. The realized value basically is known to the seller. Question is it profitable for the seller to share some of this information with the buyer to extract more surplus? I'm giving you an example that how in real life you may have to depart from Meyerson's model, right? This particular structure is actually, there are many applications on this, right? I would just like to point out a few things, and I would be more elaborate on these things later when I kind of give you some details about the model. Think about online shopping. What happens is that cached data are collected, right? Whenever I do some online shopping, the cached data are generated and they are collected. Another thing, please keep in mind, position auctioning, which is very much in the news thanks to Google these days, right? Whenever I search for some particular products, there will be some advertisements which also appear on the Google search, right? And they will be displayed in an order, right? On Google, on Yahoo. And this order, in which order one advertisement will come, this is auctioned, right? We know about this. Is called position auction. Just keep these two things in mind. I'll come back to these examples. Let's go back to the model that I was interested in. Let us form a deviation from Meyerson's model in this way. Let's assume that there is a presence of a third party. This third party can give some information about the item to the bidders, right? And this third party, what kind of information third party will give to the bidders, or the way the third party would behave, this is outside the control of the seller. So this is the information asymmetry I'm talking about. The seller knows the type of the good she is selling, right? Bidder only has partial information on the item type, which I was talking about, right? That the item can have different types, and the realized type is only known to the seller, right? In that kind of a model. But now suppose this third party that we are kind of incorporating in the environment, this third party also has some information, right? So the bidder is very unsure about the item type, right? So there is some distribution that only the bidder would know, but the bidder doesn't really know the realized value. But in addition to the prior over this item type, the bidder now obtains a signal about the item type from a third party. We are complicating the Meyerson's model in this way. There is a buyer, there is a seller, right? And the buyer is unsure of the type of the product, right? Seller knows about it. And as I already kind of talked about, that seller might want to leak some information to the buyer or not. That's another question. But there is now a third party who has the information about the type and can leak this information to the bidder in the form of a signal, right? And what this third party would do, how this third party would signal the type of the product to the bidder, this is outside the control of the seller, right? So seller can anticipate the signaling scheme used by the third party, but the seller doesn't really know the realization of the signals because it is being designed by the third party. Now the question is, again, this model, do you see a real life example of such a model? Yes, ad auctions. Here is how, right? Google is the mechanism designer, suppose, right? Google is the mechanism designer, and the mechanism designer is selling an ad auction slot, right? And what do you mean by selling an ad auction slot? Basically, in which order the ads will come. And who is the advertiser here? Let's say Myntra. So Myntra wants to advertise on Google, right? Whenever a consumer is going to search for a product, let's say an apparel on Google, then there will be some sponsored search items appearing on the page, right? On which position Myntra will appear. For that, Myntra has to actually bid. That's why the Myntra is the advertiser, right? And the mechanism designer is Google, right? Now the thing is, advertiser, Myntra, has incomplete information about the users targeted by the slots. What do I mean by this? This is very crucial, right? Slots. What are the slots? Slots are nothing but the orders, right? In which order the advertisements are appearing. If you have noticed, whenever you put in some keyword, then suppose an apparel, let's say a t-shirt, there will be sponsored ads and they will come in an order, right? What Myntra doesn't know fully is that the consumer, let's say me, I am actually visiting Google, I am keying in some apparel search, right? And there is some sponsored search coming up on the screen. What Minter doesn't know is that, what kind of consumer I am cognitively. Am I paying the maximum attention to the advertisement which is coming on the top, or I am that kind of a person who pays a lot of attention to the ad which is coming towards the end? So the order in which the advertisements are appearing, that matters to me, and this is very, very idiosyncratic to me, right? It depends on my type as an individual and as an individual consumer, right? Or as an individual, person who is making a decision about which item to pay more attention to, right? In fact, a huge literature is now emerging on the basis of this rational inattention thing, that I don't want to pay attention to the first product. This is misleading, right? So the consumer is actually making an attempt to kind of, nullify some effect which is being imposed on him or her, right? So that's a different literature, but this is coming to the focus very, very much. So this particular information is unavailable with the advertiser. But who knows about this information, that what kind of consumer I am, whether I pay a lot of attention to the first advertisement or the middle advertisement or to, which is appearing towards the end, right? Data providers, which is providing me the data, and what they do, they continuously track me, uses cookies, cached data, right? So they have some idea about what kind of person I am when I'm searching, where I'm putting in more, attention. Not only attention is just an example, but many other attributes, right? This information is very crucial to Myntra, and Myntra would like to know it. So apart from this, mechanism designer Google, who may also know about me, that what kind of person, what kind of decision maker I am, my data provider also would know who is the third party, right? Here is the model. The model is, I'll just quickly go through it. How much time do I have? Okay. So, possible types of item is N, and pi is a publicly known prior probability distribution, and there are M buyers interested in the item. So one of these buyers is Myntra, basically, right? Item is what? Item is basically one slot, right? Any buyer's type is VI, value vector for different types, and it follows some independent distribution, DI, right? You can understand this is just a kind of, in some way, we have tweaked Meyerson's basic model, right? In some way to fit this particular structure. And the seller seeks to maximize the revenue, right? There can be two scenarios. One is that neither the seller nor the buyers know anything about the item type, right? And in that case, there is only prior probability distribution, and this is very standard Meyerson's revenue optimal auction, right? Second thing is that the seller knows the type of the item, and she can actually use some signaling scheme or device to tell that, look, there are N possible types, right? So from there is a mapping Q on the distribution over a set of signals, capital S, right? So this option is available when the seller knows the type of the item, right? So what the seller can do, the seller can actually send out a signal, can design a signaling scheme, right? After sending this signal, the seller can proceed to auction the item. So basically, it's a kind of a combination of the signaling scheme and then auction to optimize the revenue. So this is optimal augmented auction, right? This scheme is available to the seller. Question is it at all useful for the seller to reveal some or all information, in the sense that whatever the seller could do by just following a simple maximization of surplus kind of a thing, right? Following the Meyersonian principle, does it really help the seller to reveal some or all information about the type? Does it bring some extra expected revenue? No, it doesn't, right? The insight is this. Whenever, so think about it, what is the situation? There can be N number of K number of types, which is uncertain, right? There is actually a direct equivalence between this kind of a situation and multi-item auctions, as if you are auctioning, you are participating in a multi-item auctions, right? It's exactly a direct correspondence. And as we know, for the multi-item auctions, you don't really need to reveal any information, in the sense that by revealing more information, you don't really gain anything. Right? You can maximize your revenue using a stupendously complex mechanism, which involves randomization, right? Basically, the buyer has to choose among some infinitely many lotteries. It's not too useful. This is the criticism against mechanism design, unfortunately, that this kind of a mechanism, when you are designing and you are asking somebody to choose from infinitely many lotteries, choose one lottery, it's not too useful, unfortunately, right? And because of this criticism, a stream of literature has come up, right, where something called a simple mechanism, right, has come out, where the idea is that don't have to really complicate the mechanism this way. What you should do, you just sell these different N items separately or bundle them. Definitely, this simple mechanism cannot match up to the optimal revenue collection. What you can do using this theoretically, using this complicated mechanism where randomization is involved, where buyer has to actually choose one lottery from infinitely many, right? That will indeed extract the maximum surplus. But simple mechanism cannot. But simple mechanism is actually indeed implemented. You can actually try to implement it. It's simpler. That's why it's called simple mechanism, right? What you are doing, you are just selling N items separately or bundle them. That's the idea. I'm not getting into too much details, right? Now, in the absence of any third party, here is the result regarding simple mechanism. In any market where the buyer's valuations are additive and arbitrary independent item value distributions, right? Either selling every item separately or putting them in a bundle, it generates at least a constant fraction of the optimal revenue. As I said, it cannot earn the same optimal revenue in expectation, but it guarantees that at least a constant fraction of that optimal revenue would be generated or more. Right? It's not a bad result at all, in fact. What happens if there is a data provider? That's the question. That's where I was actually coming to. In the presence of a data provider, the moment you bring in a data provider who signals information about the realized item to the bidder, the expected revenue of the better of this item type pricing or item type bundling, whether you are separating, you are selling them separately or bundling them, is no more than a fraction of the expected revenue of the optimal mechanism. Look at the difference between these two results. In one case, you are actually ensured of a minimum threshold of revenue, a constant fraction of the optimal revenue or more. And here, the moment you are bringing in the data provider, it's rapturing that thing. It's saying that you cannot exceed this. In one case, you are getting a lower bound, the other case, you are getting an upper bound, right? In the second case, when there is a data provider. So the third party presence raptures the implementation of the optimal revenue, loosely speaking, right? It's sort of a negative result. And definitely more research is required, right? So, but this is again a very evolving area in mechanism design, when the third-party involvement and the information leakage, especially in this kind of ad auctions and all, are coming to be very crucial, right? And definitely, it's an area where more research is not only required. I mean, it's very interesting as well. References, simple mechanism started with Rubinstein. By the way, this is not Ariel Rubinstein, it's somebody else. Everard Rubinstein, actually, it's a theoretical computer science guy. And Hart and Nishon is the classic, right, 2013, right? This paper kind of introduces simple mechanisms for multi-item auctions and prove that the fraction of the optimal revenue is guaranteed. They prove it. Babai of 2014 is another one, right, in that way. And the recent advances are in this, Daskalaikis et al. And, this particular paper. By the way, I think I have one paper has been missing here. Anyways, I can share it. Not only this, there is another paper which is written by Ekai, right? So, yeah, so that's all. That's all I had to say. And I think, 6:40. So I think I'm kind of maintaining the time as well. So I'll be happy to receive questions if you have any.
Saptarshi,
Yeah.
from an optimizer's point of view, I just was looking at what you were telling at the very beginning of this choice function, and you're trying to do a set. The C of A is set of all x, such that x is bigger than z, and so it's kind of upper level set in terms of the preference.
Mm-hmm.
So you are defining a kind of a correspondence given so means I'm trying to say that in optimization, this said for few years now, not a few years, maybe 10 years, there is a stream which has come up, but I don't think how much the computational aspect is there or not. I don't think much, but it has a lot of explanatory powers. It's that why are you talking about utility functions? Because you want to avoid that correspondence business. Definitely. But you can go ahead with that thing and develop. There is something called uh, correspondence optimization, maximizing a correspondence. How
Yeah.
would you talk about it? What do you mean by the solution? There are kind of Pareto type definition. So, but that has a lot of explanatory powers in many cases. I do not know whether in your situation whether that kind of thing can actually give in some more insight. I have no idea, but it appeared to me that there might be a link which is not yet explored, of course.
I see. I understand. So what you are trying to say, I think, I don't know. I mean, if I have understood correctly, is that see here, first thing is that yes, you are right. We are dealing with function. So if you allow for correspondence of the multi-valued set and all, you have to relax the preference relation as well. You can't make it strict, right? You have to allow for indifferences, right? So in fact, you can generate multi-valued sets just by allowing for indifferences, right? And bringing in different sorts of lotteries and all these things to break the ties and all these things, right? And this is done in stochastic choice literature typically. But what you are trying to say is that if I am kind of indifferent between two alternatives which are both Pareto but directly not comparable, then I include both. Is that correct in that kind of a situation? Right? Yeah. I mean, I don't know. I don't know of any literature, by the way.
So of course, that kind of you means, for example, you take a what would I say? So I take a commodity bundle X, and this X is mapped to many of these sets of this CA type. So can what kind of map is that? Suppose you have those maps. So given an X, I'm taking X is mapped to those set. So X is not mapped to a point, but X is mapped to a set where such that it is mapped to all the elements which are preferred over it, something like that.
Okay.
So
I see. I
do not know.
understand.
I was just thinking that.
No. What you are saying basically, this is very much in line with what Howard Simon proposed, like satisficing kind of thing, right? You have some alternative at above, so you never optimize fully, right? I mean,
what can we do with such a correspondence? Because there is a tool now which is more of an explanatory power. I don't think that has huge computational power because you don't compute with set value maps. It's abstract.
Right.
So, but it has a lot of explanatory powers. So it can give more insight possibly. That I have no idea. But maybe we can talk it out later on sometimes.
Yes, absolutely.
May I ask one thing? If time,
yeah, sure.
Yeah.
Yeah,
So
I think there is time.
Yeah. So during your talk, in your first talk, you mentioned that the experiments which we are creating are binary. If we have like 3 alternatives, then it creates some a problem. So I'm just trying to connect that observation with the fact that you also shown us a theorem that a similar theorem is true with the linear budget, right?
Yes.
So am I correct that in the linear budget, in the sense the classical thing, so there we have infinite combinations to choose from. So means that if we choose from just 2 or from infinite, things are fine, but if we go 3, then it creates a problem. So just wanted to know like the words. So if you could.
No. So the idea is, look, so the idea is that, by the way, so my presentation is gone for some reason. I don't know. Okay. So anyways, I think I don't need the slides now. So am I audible?
Yes.
So the idea is a bit different. The thing is that whenever you are taking these binary sets, the binary relation can be computed very easily. The moment you are choosing from, let's say, ABC, you are choosing A, right? So you can't really, the best way to put it is that A bits both B and C, but what is happening between B and C, you don't really know. Just because here you are taking out the binary sets, so between AB, between BC, between AC, you are actually kind of forcing the decision maker to tell the choice. Right. So basically you are trying to kind of echo out the preference relation in that way. That's the idea of binary relation, that the binary sets. What Maskell and all they do, they use convexity. Their results are based on convexity. The linear budget sets, they are convex, right? So they use the convexity result to prove that convergence theorem. So they don't use this kind of derivation of preferences in this way, right? So it's more classical in the sense that it's more indifference curve approach. And that's why this is applicable only for budget sets, which are also, linear in their paper. It was relaxed later by this Minelli and François Porges paper, but again, only non-linearity. General choice environment you can't do, right? That is done in this setting, what I just presented.
Okay.
Yeah.
Good evening, sir. Sir, I just wanted to ask one thing. I don't know, how to frame this question, right? But I just wanted to know, just like sellers, when it comes to mechanism designing, can influence signal the consumers. Similarly, these data providers you're talking about can also, in real life, can manipulate the consumer choices, or how it works in general.
Yes. Absolutely spot on observation. And this is something which is, by the way, I don't know whether it is done or not. I think it's not done. Right. So that's why I wanted to point out that this is kind of a low-hanging fruit in terms of research, very honestly, but very strong thing, right? I think we should work in this area very, very much. But you are right. I mean, there can be so many models that the way the third-party information, this third party can manipulate, right? Remember, why this is interesting is that this is not only the seller, but the third party's presence is actually kind of changing the game entirely. It's kind of, moving the game a bit away from the seller, right? It's kind of bringing it in more favor of the buyer in some way. But obviously, the third party is taking a slice of the pie as well. But, the research is still, there are not too many works as of now.
So whenever the research being done, would it be considered fair? I mean, I just wanted to know from the consumer point of view, would it be fair then when we get to know that our choices are being, I think, molded in some or the other way in real life scenario? I'm just asking.
No. What is your question? I'm sorry. Come again.
I mean, I just wanted to know whenever the research being done, these big data providers, do you think this practice would be fair when we get to know that our choices are being, I mean, maybe it leads to a better choice anyway if the big data providers can mold us, our choices in a way. So I'm just asking, would it be counted fair, like if it ever happens? Just very curious to know in that.
I don't know. This is a very difficult question to answer. How do you define fairness here, right?
Yeah.
So if you want to understand if you are asking me about the social welfare, right? From that angle, I believe that it might be the case that if you model it in this way, that some surplus, some welfare it's a kind of welfare transfer thing, right? If I am losing something, it's actually going to you and not in a magnified way. So it could be just a transferable utility kind of situation. But I think what is more important is to understand whether this is anti-competitive or not. At least from the practical point of view, this is the objection against Google's search engine, right? The advertisements are put in a way, or the search items are displayed in such a manner that it's highly manipulated to the brands which are in favor of Google, right? So it kind of impedes the competitive practice, right? So in that way, I believe in any kind of manipulation would ultimately render the welfare to be lost, right? Because if it kind of induces some sort of lack of competitiveness, right? But there could be various such angles. I'm not sure. It depends on the kind of way we want to model it. But these are all open areas. Yeah.
Thank you so much, sir. Thank you.
Saptarshi, I want to ask you a mathematical question. So you spoke about this convergence of preferences in the theorem. So how do you define that convergence of a sequence of preference to some preference?
You define what? Define the...
What do you mean by the convergence of a sequence of preferences?
No,
you must have a mathematical definition, right? So what is that? I don't know.
They simply, they define a metric, right? Which so the way they endow the topology, they can use Hausdorff metric, right? Right. So between any two binary relations, right? So they just simply define the entire this sequence, convergence of sequence in terms of that metric. That's all that. That's
So
all.
basically, in terms of the Hausdorff distances.
Yes, absolutely. They just reduce it to Hausdorff distances, and that is fairly general. So,
So I just wanted to know, right?
Yeah.
Because preferences are kind of sets, so you can take the Hausdorff distance, right?
Yes, absolutely.
That's
One small question. So in the first part of your presentation, so where agents report the agents somehow establish their choices, and from that a designer comes up with the underlying ordering. Is there any research done regarding strategy proofness type of thing there, where agents might think what should I report from there, how the preference is calculated, and can the agents gain by misreporting or something?
You mean
revealing preferences? Yeah. First
first
part,
part.
can the agent be strategic about revealing their preferences?
No, unfortunately. So that's a good question, by the way. It's like, whenever I want to conduct an experiment, then the subjects should think about that whether they're being manipulated or not, or they can manipulate it. No, I don't think there has been any research on that, Abhinava, so far, at least not that I know of. Yeah.
Thank you.
Abhinav is the director. Can we now ask the director to give his address?
So, is he here?
We are actually looking into it. So we have asked Darsh if we can get the director now.
Yeah, that would be all right, actually. Oh, it's pretty interesting that they were using Hausdorff distances. That makes more sense, actually. So the metric that you in the metric space, so the metric is defined. How are you defining a metric space? So what is your X? X consists of just some bundles, some points.
Bundles. Yes.
So how are you defining a metric there?
There is detailed description, in the paper. I mean, so they have actually endowed the topology with some properties such that, all these things boil down to a topology where there is Hausdorff distance you can apply, right? And if you just take, let's say Euclidean space, n-dimensional Euclidean space, right? That's one example, but they have generalized it fairly.
N-dimensional Euclidean space is obviously one of the best examples, no doubt, because in reality that is what we would have.
Ultimately, all the choice models, they typically take that into account. So, that's the best example for them always.
Preference means a kind of relation.
Yes.
Or in fact, I can can think of this way. So for every n, bn, you have a un, which is a utility function linked with the
Obviously,
preference.
that is
now
true.
I can say that I can think of un as a sequence of functions which converges to some function u.
Yeah, absolutely.
And the corresponding preference is the limit of the sequence of preference.
Absolutely. You can remember, but there is a problem. One particular preference relation can be actually represented by infinite number of utility functions.
Yeah.
So, the backward induction that you are applying, that could be problematic, because the utility function that you are taking might approach in the limit to some utility function, but you don't really know whether that utility function is representing only one preference relation or more than one. So that's a problem, no?
Yeah, there is a unique issue.
Uniqueness issue is there. Yeah.
No, but because here the maths must not be very straightforward, specifically in regards to convergence and all. And
no, it's not. It's how
the topology is chosen, and then what you have induced and all this kind of thing.
Yes. Those are a bit involving, but fairly general though. What I like about the paper is that those properties are applicable to many economic applications.
Obviously, it's very general. That's right. No, it is always on a commodity bundle. Means it's not that given a commodity. It could be between the commodity which is not like X or Y. It could be anything.
It could be anything. It could be anything.
Choice of between which card to choose.
Yes, yes, absolutely. Absolutely. It's that general, indeed.
Yeah, it has a kind of that kind of flavor. Yeah, I'm also thinking how whether if you take a sequence of utility function, whether see the sequence of the sequence of utility functions, if they converge, they will converge to a unique function, and whether that function would actually be a utility function or not would be again a question. That is a issue, right? So, no, this is a very typical issue. I had also sent a paper to you, remember, trying to.
Yes, I remember that.
Douglas issue, actually.
Of Douglas, yeah.
Yeah, this is a very, very strange. I am quite intrigued and quite troubled by this whole thought that give me a utility function and I can't design a preference. I cannot say, okay, if you give me these objects, I will actually choose. This will be the choice structure. That's very strange that we can't do it.
So, no other questions, probably, right?
No, your time. So we know what's the
we are waiting for the director. Dibabati, you can go ahead.
Yeah, so no, we haven't been able to get in touch with the director. So I think we'll have to get started. So we'll just take a short break, and maybe we can all just get some tea, coffee, and then we'll keep this meeting live, and we'll come back and join at say 7:05 for the next talk.
Okay, sure, done.
Sure, ma'am. Thanks, Saptarshi, for this very interesting talk and discussion. And
Thank you.
I think given that we have some time, of course, I mean, if we want to get coffee or tea, please go ahead. But I think we can kind of take this opportunity to just sort of welcome you properly for the workshop here, and we hope you stay with us for the next talk and the talks that we have lined up tomorrow. And
sure.
Very warm welcome to all the participants who have joined us, and a little bit information about CMC and the workshop, I believe, is called for. Abhinava, would you like to talk about it a little bit, since we have some time, if you're there?
One moment. You can go ahead, Rui, so I can get a cup of tea then.
Okay, sure. So this workshop, as we planned, is particularly aimed at bringing to the fore the various tools and techniques which have emerged as a point of intersection between economic theory and its applications in settings, including areas like artificial intelligence. So, because there has been a lot of work happening in economic theory and parallelly in computer science. But today, if we think in terms of applications, say, for example, the kind of the two broad areas that Saptarshi discussed, where clearly, if we are thinking in terms of decision making, or we are thinking in terms of mechanisms that can generate some outcome, then an immediate application of these is in terms of say online systems or artificial intelligence, as in the example of the Google search results, where we are essentially dealing with structures such as lists, where we do have to take into account how people are going to behave when they are making these choices, how a mechanism designer can implement certain behavior on the basis of available information, which may not be complete, where there might be asymmetries, and there could be third parties which would have some information. So the interplay of economics is essential today, and there are several tools in economic theory and which need to be combined with the current research that is happening in computer science, in the development of algorithms, as well as in machine learning. So this workshop is an attempt to bridge this gap and to take this research from the academic circles into some applications in industry, so that the knowledge that we have, that does become more widely available, widely known, and widely applied. That is the only way to develop it further. So that is the kind of perspective that we had in mind for this workshop. So again, a very warm welcome to all the participants and the esteemed speakers. And Saptarshi made a fantastic opening presentation for all of us. And for, I think everybody's already aware that he is currently at IIT Delhi. And before that, Saptarshi, before that, he finished his, completed his PhD from ISI Delhi in 2011 and then pursued postdoc at Autonoma de Barcelona. And obviously, like, the area that he works in is now clear to everybody: mechanism design, choice theory, and some of his recent research that is there in implementation theory that has brought to fore the applicability of undominated strategy and the various results. I think many of us are aware of its implications for economics and the applications outside of economics. So welcome to all here. And we'll start with Umang's talk at, I think, 7:05. So, all right. So I think we'll just take a couple of minutes break now, and then we can start. Yeah, so should we start with the next session? Deepaboti? Okay,
Yes.
Umang is here.
Umang, Abhinav,
Yeah, I'm here.
Yeah.
So maybe we can get started.
Yeah, Abhinav, could you introduce?
Okay. So Thank you everyone for staying. Let me introduce our next speaker. Professor Umang is from TIFR. His primary research interest is in algorithmic game theory and computational problems and combinatorial optimizations and so on. So we are very happy to, Umang, you can go ahead.
Okay, thanks. So let me try and share my screen. This is going to be, sorry, 1 second. Is the slide visible?
Yes.
Yes.
Okay, cool. Okay, hi everybody. Thanks for staying for the talk, and thanks to the organizers for having me. Obviously, I wish that we could have been there in person, but I guess that'll have to wait for another time. So, okay, so let me just start with a few caveats. One is that so I gave, as I usually do, I gave the topic in abstract way before I actually kind of prepared the presentation. So, the contents don't exactly reflect the topic. In fact, I won't just be talking about indivisible items, I'll be talking about divisible items as well. So it's more generally a talk about fair division. The other thing I need to mention is that this is a very basic talk. It's more of a survey. I won't delve very deep into any results. I don't think there's a single foolproof in here. So it's more of a very general talk. If you need more references to read about stuff, I'm happy to do that afterwards. Please ask. Yeah, and if you have any questions in between, I can't see the screen. I can't see the chat. I can't see anybody. I can't even see myself. I hope you guys can see me. But yeah, if you need to ask a question, just please stop me and ask. Okay, so let's get started. So, let me figure out. Okay, right. And the other thing about this talk is there'll be a lot of pictures. So here we go. So right, so we want to talk about fair division. Let's just define what is fair division, right? So basically, the question we want to answer is: so we have a fixed set of agents, we have a fixed set of items, such as those shown here, and somehow we want to divide up these items amongst the agents. We want to allocate them fairly, right? And we haven't yet said what fairly is. But let's just take a look at the items over here, right? The items could be things like a house, a car, a burger. It could be money. Money is divisible, right? 1,000 rupees, somebody would get 100, somebody would get the remaining 900. It could be items which nobody really wants, but they still have to be allocated, something like washing dishes, right? Or it could be an item such as walking a dog, which could be a chore for one person. They may not want to do it. It could be pleasurable for somebody else. So it could be different valuations. It could be divisible, indivisible, and so on. Now, right, so that's the basic division of items we'll be looking at. So they'll be either infinite or finite. And within finite, we'll be looking at either items which are divisible, such as money, or indivisible, such as a car, let's say. Now, what is an allocation? So an allocation, so I'm going to use the following notation, right? This is going to be pretty fixed throughout. So N will always refer to the number of agents, right? That's a fixed set of agents. S, the script S, the curly S is going to refer to my set of items. This could be finite or infinite. And an allocation is basically a division of the set of items amongst the agents so that it gives me a partition. Right? So agent I is going to get, let's call it a bundle, is going to get the bundle A sub I. Right? Right. So and in particular, what this means is that I want each and every item to be allocated to some agent. You can't throw things away. That's not allowed. For example, this is one allocation. It's divided up among the items are divided up amongst the agents. The money is divided, let's say, between the red agent and the blue agent, etc., etc. And there are various examples. You can think of. I'm sure you can think of lots of examples where this could be useful. Let me just mention a few. One is, for example, dividing up an inheritance. Somebody left you, with a car, a house, money, jewelry, a watch, and some bills to be paid. Right, and you need to divide this up amongst the inheritors. How do you do that? Let's say there isn't a will, so somebody has to figure out how to do that. Another use case is, for example, rental harmony. So this is, so three agents have they want to rent out a house which has 3 bedrooms, And additionally, there is some total rent to be paid, right? So they now need to figure out A, which agent gets which room, and secondly, well, how do they divide up the total rent, right? So that the amount going out is whatever needs to be paid. The third thing is obviously dividing up household chores. Once they've rented the house, then they need to make it work. So there's cleaning, there's a mop and a pail. And let's say they have a dog, they need to walk the dog, there are dishes to be washed, there's food to be cooked. How do you divide up all that? Or another example is, just dividing up seats in parliament. And like a lot of parliaments will have seats reserved for particular minorities or ethnicities or what have you. For example, the Indian parliament does. Right? So what's a good way of doing that? How do you kind of ensure that people have representation in parliament? That's another example of fair division. Okay, so we haven't said much about what fairness is. So in order, to go towards that, I'm going to assume, that we have valuation functions. We have these cardinal valuation functions, and right, I'm kind of reminded of the earlier talk where we talked about utility functions as well. But anyway, so this I'm going to assume explicit valuation functions, right? And this is all given. There's nothing hidden from, from the mechanism. So every agent I has a cardinal valuation function. And basically, it's defined over subsets of the items, right? So for any subset of the items S, V sub I of S is agent I's value for that subset S. And we're going to differentiate particularly between two types of items. The first type of item is a good. So a good is an item for which an agent always has non-negative value, right? No matter what the agent already has, if you give it a good item, then its value cannot decrease. And the others are bads, which are just the opposite, right? So if you give, so no matter what an agent has, if you give the agent a bad item, then the agent's value always cannot increase, right? It may decrease. So, and then there are other, special cases we look at as well. We'd say a valuation function is additive if, if you take any two disjoint sets of items, well, an agent's value for the union of these two sets is going to be the sum of the values for the two sets. That's just additivity. And the other thing, well, this is kind of a weak assumption, which is normalization. So I'm going to assume that over the entire set of items, an agent has utility 1, has valuation 1. Right. Okay. So this is the normalization assumption. When I kind of draw diagrams, I won't actually follow this because I don't want to put down decimal numbers. But for the results and so on, let's assume that everything is normalized. Okay, good. So here's a brief outline of the talk. It's going to follow the kind of hierarchy of items that we saw. Like I said, this is going to be a rough survey of what's known about fair division. So we're going to start off with the case of an infinite set of items. In between, we'll take a segue. We'll kind of talk about applications of fair division as well. Then we'll talk about these two other cases, right? So a finite set of divisible items and a finite set of indivisible items. And as we talk about indivisible items, I'll also talk about the case of bads. For most of the talk, I'm just going to focus on goods. But when we talk about indivisible items, I'll talk about bads for a little bit as well. And then, we'll recap. I'll mention some open questions, and I'll mention some stuff that I didn't get to talk about, which will be a lot more than the stuff that I will talk about. There's a lot of work in this area. Okay, so let's get started with when you have an infinite set of items. And so this problem is also known as cake cutting. And that's how it was first introduced. And usually the set of S of items, as is often the case, it's represented as the 0, 1 interval, right? There's points in this interval. And the way the valuation functions are given is that every agent has some integrable density function f sub I. Okay? That's for agent I. And we usually assume that it's non-atomic, so there are no atoms. And for any subset of this interval, of the 0, 1 interval, the value is going to be the area under the curve, as you might expect. And clearly, this already assumes additivity, right? There are models which don't assume additivity, but let me keep it simple for right now. Let's assume that the valuation functions are in fact additive, right? And yeah.
Sorry, just one quick clarification. Given the assumption of additivity, it's like the PDF, right? So F is a PDF. Is it correct to
Yeah,
say?
that's a good way of putting it. Sure, yeah, absolutely. Good. Okay. So right, yeah, given the normalization assumption, that makes complete sense. And yeah, the way like reason it's a cake is because you can think of like radial cuts along a cake from the center, and you start from a particular position, and then you kind of like the angle is equal to whatever interval you're taking in 0, 1, etc., etc. Okay. So here's a particular kind of density function for the agents, right? And it could, it could be completely arbitrary. Density functions will look like this are easier to work with. So we'll talk a little bit more about these kind of functions a little bit later on. But let's just work with this example. So because we haven't still defined fairness, so let's kind of work towards that. Now, so let's look at this allocation, right? So in this allocation, the green agent basically gets the first half of the 0, 1 interval. It gets the points from 0 to 1/2, and the red agent gets all the remaining points, right? And it's easy to see that the value for each agent is going to be 1/2. It's equally divided. I'm going to say that an allocation is proportional if every agent gets value at least 1 over n for the bundle that she is getting. Right? Then clearly this particular allocation is proportional because every agent is getting at least 1/2 of her total value for the entire interval, which is 1. Right? N equals 2 in this case. So okay, so that's one of the fairness criteria I'm going to look at, which is proportionality. It's pretty simple. It's pretty basic. You would expect that in any fair division, you should get at least, if there are n agents, you should get at least 1 over n of your total value. Okay, so let's take a look at the second criteria. So this allocation, in fact, satisfies something else as well, which is that for every agent, you look at the bundle she did not get. Right? For the green agent, you look at the other interval from 1/2 to 1, and her value for that is also 1/2. And similarly for the red agent, if you look at the bundle she did not get. In particular, what this satisfies, so this is what is called an envy-free allocation, which is that no agent prefers what some other agent has. No agent envies some other agent's allocation, or her value for her own bundle is at least her value for anybody else's bundle. Right? So, so just to, if you look at this inequality, I have VI on both sides. So I'm looking at just what VI's value is for each of the two bundles. Okay? There are no cross-agent comparisons, so to speak. I'm only looking at bundles. And as we said, for each agent, the value of the bundle she is assigned is the same as the value of the bundle she is not assigned. So this allocation is clearly envy-free. Okay, good. Okay, so this is actually going to be another kind of very recurrent property of fairness, envy-freeness. We will be looking particularly for envy-free allocations. And we'll kind of give more properties of this later on, but let's keep going for a bit. Right, so this allocation which I have described satisfies these two properties, but something should bug you. It's not a great allocation, right? In particular, it's not an efficient allocation, and by efficiency, I'm talking about Pareto optimality, right? So if you look at this other allocation, which it's a little bit more complicated, it has more cuts in the cake. But basically, it gives every agent, the portion of the cake or this interval for which she has non-zero value, non-zero density. Right. So the green agent gets the interval between 0 and 1/4, and the interval between 1/2 and 3/4, and the red interval gets the remainder. And it's easier to check that this is also proportional and envy-free, and this is also Pareto optimal. Right. I'm sure we all know what Pareto optimality is. Just to kind of remind ourselves, perhaps, what I mean is that no other allocation has improves on one agent's allocation while keeping everybody else at least the same. Right. So another way of saying that is that any other allocation, if it improves somebody, it has to make somebody else worse off. It cannot uniformly improve the values. Okay, so this is a much nicer allocation. So maybe it's not just fairness so much which we want, but fairness also combined with, let's say, Pareto optimality as a measure of efficiency. Right? So this is kind of what we'll be going for, what we'll be looking for in terms of our desiderata for the allocations that we come up with. And Pareto optimality also by itself also means that you can't really throw away parts of the cake, right? Because as long as people have non-zero value for it, you can't really throw away parts of the cake. Okay, so I have a note over here, which is that, you know, if you kind of put pen to paper for about 5 minutes, you'll figure this out, which is that for additive utilities, such as what we're looking at over here, NV-freeness in fact implies proportionality. So if an allocation satisfies, you know, the second property we talked about, it is also a proportional allocation in that every agent will get at least 1 by n of her value for the entire interval, for the entire set of items. Okay, right. So now let me talk about applications, and it turns out that fair division is actually, I mean, people have tried to in fact come up with a whole bunch of applications for it. So this is a screenshot of the website. The website is a company called Fair Outcomes Incorporated. It's based in Boston. And what this company does is basically it uses fair division algorithms to either resolve disputes or to come up with some kind of bargains or some kind of agreements between different parties, right? So I'm just kind of reading the last line from this. Each of these systems is grounded in mathematical theories of games and fair division. In fact, this company was founded by Stephen J. Brams, who's a political scientist and a game theorist, and he is responsible for a number of fundamental algorithms in fair division. So we talked about NV-free allocations, right? So with Alan Taylor, in fact, Stephen Brams was the first person who gave the first NV-free cake cutting algorithm for n agents. Okay, so that's for n agents. For 2 agents, for a different setting, for the case of finite divisible items, he gave another procedure which has a number of nice properties, and we'll come back to this a little bit later, which is called the adjusted winner procedure. Right? So that's something we'll look at a little bit later as well. But basically, so this adjusted winner algorithm is something that was patented by NYU, and then Fair Outcomes is using this for the work that it's doing. And this is again from the website. You know what? Maybe I'll just let you read it later on. Just go to just Google Fair Outcomes, and you can kind of see how it's using the kind of algorithms that it's using. I mean, now that you know what proportionality and NV-freeness is, you'll actually recognize. You'll be able to parse a lot of what this is saying. But let me move on for now. I don't want to get stuck too much over here. The second application I want to talk about is this app. Actually, so Fair Outcomes is more monetized. It's a company. Well, it's incorporated. Split is more of a non-profit venture, just to kind of play around with fair division algorithms. So Split is something that was started by Ariel Prakachia, Jonathan Goldman, and Nisarg Shah. It's a not-for-profit. And it's used what I'm calling for everyday fair division. Things like you just want to figure out what's the best way to divide rent, or how to divide household chores, or maybe some people have collaborated on a paper, and you want to figure out, well, who gets the most credit, who gets the least credit, and so on. Or taxi fare if you shared a taxi, and so on. For these applications, it implements different algorithms. For example, for credit for papers, I think it uses the Shapley value. Right? And that's something I'm sure we've all seen. For the fair division, it uses the Nash welfare. And again, that's something we'll come back to later on. It's a very interesting website. Again, after the talk, I'd recommend that you spend a few minutes just going through it. You can even download the app on your phone and use it for you could just play around with it and try and divide up things amongst you and roommates.
Just can I ask one quick clarification?
Please, of course, yeah.
So for Shapley value, one needs to define the function V, right? That how much a person I make the contribution. So in a sense, but it's somewhat difficult to define for the contribution of the paper in a sense. So just curious that how they do it, or maybe you can take it towards the end also.
Yeah, in fact, let me take it after I've actually looked it up.
Sure,
So I'm not completely sure. No. So that's a very fair question. I mean, all of these, in fact, will require you to. I mean, I think what they do is that they use estimates. So they give you 100 points and they ask you to divide it up amongst various things. Yeah, but they probably fine tune it a little, and I'm not exactly sure how to do that. Okay. Right. So let's go ahead with cake cutting. The infinite set of items case, and we've already talked about this. We know how the valuation of agents is represented. So we talked about proportional and envy-free allocations. One of the questions which we should worry about is that, so here the density functions are nice and regular. If they are not, how do we access the agent valuation functions? I can't possibly ask for a density function at every point. So Robertson and Webb gave a query model for this, which is still used very popularly. And basically, the density functions are stored as oracles. And you can ask an oracle two things. You can either give the oracle an evaluate query, wherein you pass it an agent and some interval, some subset of items, and ask it, well, what is agent i's value for this subset? Right? So that is an evaluate query or an eval query. The other thing you can do is that you can ask it, well, how much of this cake, how much of this interval do I need to get a certain value? So the cut query passes it an agent, passes it a starting point, and passes it a value. And it asks, well, starting from X, how much of the interval do I need in order that I get value V for agent I? Right? And if these queries, if these queries make sense, then we can kind of analyze, the complexity of an algorithm in terms of how many queries does it take to find a fair allocation. Right? How many eval or cut queries does it take to find a fair allocation? Okay, so let's take a look at one simple procedure for finding a fair, a fair division of a cake, which is, it's called the cut and choose protocol. And again, it's something that is fairly widely known, which is that basically one agent cuts, the other agent chooses. Right? So let's say the green agent goes first. Then the green agent cuts the cake into two parts, which according to her are of equal value. Right? So note that this step can be done with just one cut query. Now the red agent looks at the two pieces and takes the part which is more valuable to her. And again, this is just one evaluate query. And the green agent takes the remaining part. Right? So this can be implemented with just two queries. And the claim is that, in fact, for the two agent case, this returns an envy-free and hence proportional allocation. Right? Because we said that envy-freeness implies proportionality. And this is very easy to see, but just as an exercise, let's do it. So the green value cuts the cake so that both parts have equal value. Right? So she doesn't really care which part she gets. And the red agent takes the part which is higher value for her. Right? So she is clearly not going to be envious of the other part of what the green agent ultimately gets. Yeah, it's a two-line thing.
Sorry, just one quick level. So this cut and choose may not give the efficient one, right? The example you have given.
No, it won't. So let me just go to the next slide. I think that will answer your question.
Yes.
So, or maybe the slide after this. But just keep that question. I'll just come back to it. So, but if we kind of avoid efficiency for right now, here's the thing. So proportionality, it turns out, is not too difficult. Right? There are many ways of doing it. Evan and Paz gave an algorithm which basically makes order of n log n queries, and it finds a proportional allocation. Right? So that can be done, no problem. Envy-free allocations are a whole different story. So I said Brands and Taylor had given an algorithm. The algorithm makes an unbounded number of queries. And this was reduced to this, horrible looking number. I think there are 5 powers of n over there. But this is actually the best known algorithm we have for finding an NV-free allocation. And you could ask, well, do we really need to make these many queries? The answer is we don't know. The only thing we know is that you have to make at least n squared queries to find an NV-free allocation for cake cutting. So there's a huge gap, and an obvious open question over here is, well, how many queries do you really need to find an NV-free allocation? Okay, so to get back to what was asked, well, what about efficiency? What about Pareto optimality? And the problem is that, because we don't have nice regular density functions, it turns out that the Pareto optimal allocation cannot be found with a finite number of queries. And you could always have irregularities which kind of preclude this. So this you can't do it with a finite number of queries. Well, what about existence? I mean, okay, so Pareto optimal allocation obviously exists, right? I mean, say an allocation which maximizes the social welfare, that will also be Pareto optimal. What about if we look fair and Pareto optimal allocations? Right? And fair can mean either proportionality or NV-free. So this question gets interesting, and we'll spend a few slides on this. So it turns out that, in fact, there exist allocations which satisfy both NV-freeness and Pareto optimality. Okay. Remember, computation, we said, is not our concern right now because we can't do that in finite number of queries. So what about existence? So it turns out that this does exist, and it's given by what is called the competitive equilibrium with equal incomes. And this is very similar to market equilibria, but I'll define it. So that's what the next slide is. So what is this CEEI? So in CEI, we have n agents, and each of them has an initial endowment of 1. The unit doesn't matter. Let's say 1 rupee. And again, we have a set S of items. It's a 0-1 interval. And competitive equilibrium with equal incomes consists of an allocation as well as prices. So that, firstly, the competitive equilibrium part means that, like another, okay, so it's I'll parse this, but basically what it's saying is that every agent is getting informally the maximum bang for its buck. So what that means is that if it's allocated A sub I, if you look at any interval of its allocation and any other interval A, right, the ratio of the value to the price that the agent is paying is at least is larger in A prime than what it is for A. Okay? So what it's getting has to have higher bang per buck than any other interval. So this is the competitive equilibrium part of it. And the equal income part of it means that every agent should be spending exactly its endowment, which is 1. Okay.
Can I ask a clarification question regarding the previous slide?
Oh, sure.
So here with the negative result, so here cannot be found with a finite number of queries. So these corresponds to those 2 types of queries that you listed before. Like
yes. Yes.
So there are no other possible queries that one can make.
I don't think so. Basically, because the point is that you can hide these very high density within, like within an interval. So unless you kind of make smaller and smaller and smaller queries, you won't find exactly which part is best.
Okay.
So my guess, so my guess is that you can't really come up with a reasonable query model which would allow you to find a PO allocation with a finite number of queries. But I would be happy to be proved wrong.
Thank you. Thank you.
Yeah. Okay. All right. So so we've mentioned this competitive equilibrium with equal incomes, and so here's what's known. So 2 things. Firstly, actually, for any cake cutting instance, this CEEI actually always exists. And the nice thing about such an outcome, such an equilibrium, is that in fact it is both NV-free and Pareto optimal. Right. This is known as Weller's theorem. It was strengthened later on by two other authors, Sigal Halevi and Ziklai. I'm sorry, I can't pronounce the other author's name. I should have looked that up. Anyway, I'm sorry about that. But yeah, so the basic theorem is due to Weller, and then it was strengthened some years later on as well. But the interesting part is that yes, an NV-free and Pareto optimal allocation does exist, and it has this nice connection to market equilibria, and that is something actually which was exploited in later papers as well. But there's even something nicer. So, let me, let me define the Nash welfare for me. The Nash welfare for an allocation is just a product of agent valuations. Right? And in fact, it turns out that the allocation which maximizes the Nash welfare is also, in fact, A maximizes the Nash welfare if and only if A is a competitive equilibrium with equal incomes. Right? The two allocations actually coincide. Right. So other than finding prices and all of that, I actually have a much nicer way of finding an NV-free and Pareto optimal allocation, which is just to find the allocation which maximizes the Nash welfare. So can we compute this? Right. As I said, no, in general, no. But if you have like simpler density functions, right? For example, if all agents have what are called piecewise constant density functions, such as what's shown over here, then in fact a Nash welfare maximizing allocation can be obtained with a polynomial number of queries. Right? In fact, it can be done in polynomial time as well. So we can do this, quickly by CS standards. Right? So piecewise constant density functions are nice. Okay. Right, so that's all I wanted to say about the infinite items case. I'm going to quickly talk about the finite set of divisible items case, and then I'll jump into what I'm actually supposed to talk about. So, okay, so divisible items, right? So divisible items, again, you have n agents, you have a set S of m items, right? So now it's a finite set of items. And an allocation, so AI, which is, let's say, the green agent's allocation, is actually a vector. It's a vector with m components, one for each good, and it tells me what is the fraction of that good that agent I gets. Right? So xij is the fraction of item j that agent I gets. And again, the constraint is that every item has to be fully allocated, or that the sum over all agents of xij must be 1. And typically, again, over here, so let me assume additivity. And so now valuations are much more simply represented. They just, for every agent and for every item, I just specify the agent's value for that item. So Vij is agent i's value for item j. And her value for her entire allocation is exactly what you think it is. I'm not going to pass that. Okay, so the nice thing about divisible items is that in fact it can be modeled as cake cutting with piecewise linear valuations. Right. So basically, that for an agent, you just kind of line these items up, and an agent's value for that piece is just whatever the density function is, it's constant. So which means that all of the positive results I have for cake cutting hold. So a Nash welfare maximizing allocation can be obtained in polytime. Nash welfare implies that I'm getting an NV-free and Pareto optimal allocation, and for additive utilities, NV-freeness implies proportionality. Right? So all of the criteria I have, I can satisfy. I can find such an allocation in polytime, all as well. I'm just going to take 2 seconds to talk about this adjusted winner algorithm. So it's restricted to the 2-agent case, right? But it turns out that 2-agent cases are pretty common, right? Like one of the examples that if you look at the Fair Outcomes website, one of the examples given over there is divorces, right? So then that's 2 parties which have to divide up among whatever the property is, and there are various other examples. And the nice thing about adjusted winner is that it satisfies a number of properties. It is EF and PO, right, as we would like it to be. It satisfies another property we haven't talked about, which is equitability. And I'm not going to explain what that is. The third property it has is that actually at most one item is fractionally allocated. Everything else is equally allocated. At most one item is fractionally allocated. You can't choose which item that is. It could be the house, unfortunately, but it will be at most one item. And I mentioned about the patent and its usage. I'm not going to describe what this is. Again, this is something we can do maybe offline. Right, so let's jump into indivisible items. Okay, so here's the setting. Again, n agents, m items. An allocation is basically a subset of the set of, it's a partition of the set of items. And in the additive case, again, there's a very simple description of the valuation functions. For every agent, for every good, Vij describe agent i's value for that good. By the way, I'm just going to pause for 2 seconds, and in case anybody has a question or something. I realize I've been going a bit quickly, so I think I have time. That allows me to have some water as well. Okay, so let's keep going. Now let's also look beyond additive valuations, right? Because we don't really expect valuations to be additive most of the time. So instead, we can also represent it as value over subsets of the items, right? Where for some subset S, Vi of S is agent i's value for that subset. So we could look at more general valuations as well. For example, valuation functions could be single-minded, they could be submodular, they could be subadditive, what have you. If you don't recall what these are, it's fine, don't worry about it. We won't really get into technical details. Okay, so now what do we want to do? So we talked about two fairness considerations, and we talked about Pareto optimality, right? So clearly we would like an allocation which satisfies all of these. And I just want to point out that this NV freeness implies proportionality. It only holds for the additive valuations case. Beyond additive, it may not hold. But let's just stick to additive valuations for now. So with indivisible items, things get stuck. So far, we've been doing very nicely. So let's take a simple case where there are two agents and just one item, right? And both of them have value 1 for this item. It's clear that a proportional allocation does not exist. The item is indivisible. It has to go to a single agent. The other agent gets value 0 from her allocation. And that's clearly not proportional. So we need to, do something about that. But what does exist is an allocation maximizing the Nash welfare. Right? So this still clearly exists. So maybe you want to ask, well, okay, so let's look at this alternate allocation, the max Nash welfare allocation. What properties does such an allocation have? And clearly, this is Pareto optimal. So there's a slight detail I'm missing about, because in this case, for example, over here, the allocation is going to have value 0, right? But let me just ignore that for right now. Let's assume that the optimal Nash welfare is not 0.
Can I ask one clarification at this moment?
Please, yeah.
So NV-free allocation may not exist, but suppose when they exist, even then you are saying that it does not imply a proportionality.
If you have non-additive valuations.
Okay. If we have non-additive, okay. Yeah. In the non, sorry, I missed that.
Exactly.
Okay, thanks.
So if you have submodular or subadditive valuation or something, then it may not imply proportionality. Okay, right.
Can I ask one more clarificatory question?
Of course,
regarding this example where you have to partition, just give one indivisible object to one among two agents, where you said that one agent in every allocation will get value 0.
Yeah.
So every allocation would satisfy this product. So every product would be 0.
Yeah. That's what I'm saying. So typically what you would do is, if it's 0, then you would try and just look at the agents which have non-zero value. So you just look at that subset of agents, and then you try and maximize the product.
Okay.
Yeah. So yeah, I mean, there are ways to get around that. I'm not getting into that detail right now. That's all. Okay, great. So, but I want to I want to say that in fact this Nash welfare is actually a really nice thing. So and it's, you know, more generally what we can talk about is the p-mean welfare, right? So in which, you know, I take the valuation of every agent, I raise it to some pth power, I take the average, so I divide it by n, and I raise the whole thing to the power of 1 by p. So this is what I'm calling the p-mean welfare, and this has a number of nice properties, right? So p equals 1, we just get the utilitarian social welfare. And again, I realize I'm missing an averaging term. The 1 over n should be there as well, but I mean, the allocation is the same, so let's ignore that. For p goes to minus infinity, this is this is the maximum welfare or the Rawlsian social welfare, right? We want to maximize the minimum valuation for any agent. And as p tends to 0, what we get is the Nash welfare, which, you know, we've been kind of talking about, right? So basically, the Nash welfare has this nice thing and kind of balances between the utilitarian, between these two extremes of welfare, where you're looking at the sum versus by you looking at just the minimum. That's nice. It also has a number of other nice properties. So Mola kind of describes these properties. It satisfies what's called the Pigou-Dalton transfer principle. And again, I'm not going to describe what that is. You know, again, I can do that offline. It's scale-free, which means that if you kind of multiply an agent's values, all of an agent's values by, let's say, some constant c. So, you know, the normalization is short, but okay, let's forget about that. The optimal allocation does not change, right? So it's scale free in that sense. In fact, it is the only welfare function to satisfy both the points above.
So is it C for everyone, or can we have CI like?
You can have CIs for each agent. Yeah.
CI.
Each agent can be scaled differently. As we saw, in the divisible case, the max Nash welfare corresponds exactly to CEI and gives us EF plus PO. And in fact, the Spirit app uses the max Nash welfare allocation for the fair division of goods. So it's all nice. So, but let's get back to our problem, right? Our problem is that these two fairness guarantees we were looking at, one of them at least does not exist. Okay, so let me focus for a while on the goods case. So what we do is we define a relaxation. So this is the relaxation we define. We say that allocation is prop 1 if for all agents I, there exists a good G, so that if I now give, if I include that good in the agent's bundle, right, then her value is at least 1 over n. Right? So she may not be satisfied with just a bundle as it is, but there is some good which I can add to her bundle which causes her value to become at least 1 over n. Right? So this is prop 1. The 1 is because I'm adding one good to her bundle.
And this G is same for all, right? Just to be sure.
No. If for all agents, there exists a good G.
So then it should be GI, right? Not G.
Sure. Yeah. Let's say, let's call it GI. Right. It doesn't have to be the same across agents. And clearly, so this is a prop 1 allocation, right? So now I can assign the strawberry to any one of the two agents. The other agent doesn't get a strawberry, but now G is the strawberry. If I gave the agent the strawberry, her value would be 1, which is at least 1/2. This is prop 1. Similarly, I can define EF1. There's a slight so for envy fairness, I'm comparing two agents, right? I'm saying that I should think her bundle is the best. Right? Now I'm saying I should think her bundle is the best as long as I'm allowed to remove some good from agent J's bundle. And again, to kind of head off the question, this G can depend on both I and J. For all agents I and J, there exists some good, we can call it GIJ, in agent J's bundle, so that if I take out this good from agent J's bundle, agent I is fine. Agent I says, okay, my bundle is better than agent J's bundle with that good removed. So here's, for example, an EF1 allocation. Again, I can assign the strawberry anywhere because currently the red agent envies the green agent, right? She would rather have what the green agent has, but I'm allowed to remove a good. So if I remove the strawberry, then the agent says it's fine. I don't really prefer what the green agent now has. Okay, so hopefully this makes sense. And again, the nice thing is that in fact, for additive valuations, EF1 implies prop1, right? So if it's envy-free up to one good, it is also proportional up to one good. Great, but now does there always exist an EF1 allocation? And here's the really nice thing. I mean, that this max Nash welfare, it kind of delivers even in the indivisible item space. So so we know, for example, for additive valuations, if I look at the max Nash welfare, then in fact this satisfies EF1 and Pareto optimality, right? And therefore it also satisfies prop1 and Pareto optimality. So if I can find the max Nash welfare allocation, I can, then I have my fairness as well as my efficiency satisfied. Great. And as I said, in fact, this is what is used in the Spirit app for fair division of goods. The problem is that computationally, actually, this is pretty bad. So the best algorithms we know for computing the max Nash welfare take exponential time. And in fact, there's a theorem which says that APX hard. I won't describe what APX hard means, but basically, we can't do this in less than exponential time, as far as we know. But the point is that, okay, but finding a max Nash welfare is not the only way to find an EF1 plus PO allocation. It turns out that we can use this connection of market equilibria to find an EF1 plus PO allocation more quickly. Right? So recall that we said max Nash welfare will give me EF1 plus PO, right? But the converse is not necessarily true. Right? It's not true that every EF1 plus PO allocation must maximize the Nash welfare. Right? So EF1 plus PO turns out to be easier. There we go. Sorry. Then, in fact, it's been shown that this can be found in pseudo polynomial time. And the pseudo polynomial just means that if all the numbers involved are small, if all the valuations are small integers, then in fact this can be done in polynomial time. If my valuations are not too large, they're not exponential, this is all fine. So great. Okay, so what I'm going to focus on now for a bit is just EF1 allocation. So I'm going to look at some algorithms for just computing EF1 allocations. Right? So I have a set of agents, n agents, n goods, and I want to find an envy-free up to one good allocation just to kind of get a flavor of what algorithms for this look like. Here's a very simple algorithm. It's just round robin. What does round robin do? It does exactly what it says. I just arbitrarily order the agents. Let's say blue and then red and then green. In this order, one by one, the agents pick the most valuable item they have remaining. Right? So let's say the blue agent's turn, it picks the pumpkin, that's what it likes most of all. The red agent picks the orange, then the apple. The blue agent picks again, it picks the lemon, that's what it likes most amongst the remaining items, and so on and so forth. And we're done. Okay? And this allocation is EF1, right? And let's just quickly kind of see why that is. So look, okay, so there's a lot happening on this slide, but let's look at what happened when the green agent chose so let's just compare the green agent and the red agent, right? Those two agents. Now, when the green agent chose the apple, the tomato was available, right? So she could have chosen the tomato also. She preferred to choose the apple. So she prefers the apple to the tomato. Similarly, when she chose the corn, the strawberry was available, but she preferred choosing the corn, right? So she prefers the corn to the strawberry. Right? What this means is that she prefers her own bundle, the apple plus the corn, to the tomato and the strawberry. Right? Which means that from the orange agent's bundle, if you remove the orange, sorry, there's a slight typo in the slide, I'm realizing. In the bottom expression, the second V sub G should be, no, sorry, actually it's right. I apologize. Sorry. Yeah, so for the green agent, if you now from the red agent's bundle, if you remove the orange, then she actually prefers her own bundle, and therefore this is EF1. And similarly, you can do this for any pair of agents. If you just remove the first item assigned, then every agent prefers her own bundle to that agent's bundle. Right? Sorry, this was really fast, but again, it's something that if you spend a couple of minutes, you should figure it out. Right, so round robin gives you F1 for additive valuations, right? And we want to ask, well, what about other valuations? What about submodular, subadditive, and so on? So well, one of the things is that we can't even now look at the max-Nash welfare, because this max-Nash welfare gives us EF1 plus PO. That again is only true for additive valuations. For submodular, subadditive, it may not hold. So actually, but there's this nice result which gives an algorithm exactly for this. In fact, for arbitrary valuations on goods, it says if all items are goods, then what's known as the NV cycle elimination algorithm gives an EF1 allocation. Right? It doesn't matter whether it's subadditive, submodular, arbitrary, as long as all the items are goods, right? As long as they have positive marginal valuation, this algorithm will give you an EF1 allocation. Okay. And okay, so I'm going to spend a few minutes on this algorithm. So what this uses is the concept of something called an NV graph. It's a very natural concept. Basically, it's a graph which shows who NVs whom. But let's just put this down formally. So supposing you're looking at some partial allocation, right? Some of the goods have been assigned, not all of them. These 4 have been assigned, all the other 4 are remaining. In my NV graph, the agents are vertices, and there's an edge from agent I, so it's a directed graph. There's an edge from agent I to agent J if I NV is J. Okay? That is, if I thinks that what J has is preferable to her own bundle. So this could be, for example, what the NV graph looks like. The green agent thinks that, well, both the blue and the red agent are preferable to what she has, and the red agent prefers what the blue agent has, and so on. Right? Okay, so here's what the NV cycle elimination algorithm is. So this time you consider the goods in any order. Right? Forget, earlier you put the agents in some order. Now you put the goods in any order, and assign each good to a source in the NV graph. So a source is a vertex which does not have any incoming edge. Right? So you assign each good to a source. If you have no source in the graph, there must be a cycle. You resolve the cycle, and I'll say what that means, and then you continue. So 2 things, as I said, what does this do? So if you're giving an item, right? If you're giving a good, you don't want to give it to an agent who is already the subject of NV. Okay? You'd rather give it to an agent who is not NV'd by anybody else. And such an agent is precisely a source in this NV graph. Right? And what this algorithm maintains is that, in fact, at every step in the algorithm, the partial allocation so far is, in fact, EF1. So I have an example. I'm not completely sure if I should run through it, but let me just kind of quickly go through it. So this is the order of the items. Strawberry comes first, pumpkin comes last. So strawberry has to be assigned to a source. All of them are sources right now. I assign it to the red agent. And let's say now this is the NV. Right? So the blue and the green agent now both NV the red agent. I have 2 sources. The corn goes to the blue agent. This is now what the NV looks like. Right? So now I have just one source, which is the green agent. Tomato goes to the green agent. And now this, and let's say that nothing changes, right? Nobody has any value for the orange, let's say. Now the lemon is also assigned to the only source in the graph, which is the green agent. And that causes NV. So now the blue agent thinks, so note this kind of cyclic behavior. So the green agent thinks what the blue agent has is better. The blue agent thinks that what the green agent has is better. Right? So I have a cycle. And in particular, there is no source in this graph. There is no agent which does not have an incoming edge. So I resolve a cycle. And what that means is that I exchange the bundles along the edges of the cycle. So the green agent gets the corn, and the blue agent gets the orange and the lemon. And now these edges go away because both of them have their preferred bundle amongst the two, and so on. I'm not gonna, but yeah, you understand what I mean, what this algorithm does. Right? And then, as I said, what they show is that the allocation obtained by this algorithm is in fact
One clarification question. So, can you
Yeah.
show the step where the blue agent and green agent items were swapped?
Yeah.
So, before swapping, green
Yeah.
agent was envious of orange agent, and that would remain, right? Even after swapping.
That could remain. Like we don't know until I tell you the actual values. But
Okay.
it could be that the green agent still prefers the strawberry over the corn, for example. In
Okay.
which case that edge would remain. Yeah?
Thank
So this is what happens afterwards, and maybe the envy the green agent has doesn't completely go away.
Okay.
Yeah?
Thank you.
Okay.
Just one more
yeah,
thing. The
yeah.
theorem you have mentioned, does it hold for any evaluations, right? Not necessarily additive. It holds for any.
Yeah, exactly. That's the whole point. For additive, we have the sound hopping thing. This holds for any valuation as long as I said, all the items are constant.
Okay. Yes.
Yeah. Great. So this is such a nice algorithm that, in fact, people started thinking, well, maybe it works for chores as well. Right? I'll take maybe 5-7 more minutes. I hope that's okay.
Yes, there is a time up till 8:15. So.
Okay, cool. Right. So yeah, so people started asking, well, does it work for chores as well? Now, chores, we have to be careful because the definition changes. So let's see how the definition changes. I'm going to focus on EF1, not prop. Let's focus on EF1. So I'm going to say an allocation is EF1 for agents ij. So earlier, what was I doing? Let's say that the green agent envied the red agent. Right? Then earlier, I was removing a good from the red agent's bundle. Now, if the green agent envies the red agent, I will remove a chore from the green agent's bundle. So the definition says that an allocation is EF1 if for any two agents I and j, there exists some chore, let's say Ci in agent i's bundle, A sub I, so that if I remove that chore from agent i's bundle, then she prefers her bundle to what agent j has. Okay. You see the symmetry between the two. Right? Earlier, I was removing a good from the envied agent. Now I'm removing a chore from the envious agent, which makes sense because if I were to remove a chore from the envied agent, that agent's value would just grow higher. Right? So that wouldn't make any sense. Okay, so hopefully that's fine. And now again, trivially, I can just assign anybody the chore of washing up because the green agent now envies the red agent, right? Because she has negative utility for this chore. But I'm allowed to remove a chore from the envious agent. So if I remove mopping from the green agent set of from the green agent's allocation, both of them have value 0 for their bundles and there's no envy. Okay. So yeah, right. So there's this deceptive symmetry between the two cases. And people started asking, well, okay, so what about chores? And again, it turns out that in fact, for additive valuations, for chores with additive valuations, right? So an agent's valuation for a set of chores is just the sum over the agent's valuation for each of the individual chores. The round robin algorithm still gives an EF1 allocation. But again, we can ask, well, what about more general valuations? I mean, it could be that you're okay with washing dishes, you're okay with cooking, but the two together you just dislike doing. That describes me, by the way. But anyway, so yeah, so what happens if you have chores but with subadditive, submodular, or maybe the superadditive, supermodular, whatever it is? Then does the envy cycle elimination algorithm work? So this is what the algorithm was earlier, right? And maybe we just have to make these tweaks. maybe chores have to be replaced with, maybe goods have to be replaced with chores. And I should have put plural chores in the first replacement, but anyway. And sources have to be replaced with sinks. Right? So earlier, remember, we were giving a good to an agent whom nobody envied. Now we're giving a chore to an agent who does not envy anybody else. Right? So that's a sink in the graph. Does this work? And it turns out that it does not work. In fact, it seems so natural that a number of papers actually believe that it would work, but there are some subtleties. In fact, it turns out that the problem is in the third step. The problem is in the cycle resolution. So allocation is fine, but as soon as you resolve the cycle, things go wrong. But what does work is a slight modification. And it's kind of, slight enough that I can just put it on the same slide, which is that when I resolve a cycle, I don't just resolve any cycle. I look at the top NV graph, wherein there is an edge between I and J, only if I envy is J the most. That means I has maximum value for agent J's bundle amongst all other bundles. Right? So if there isn't a sink in my graph, then I resolve a cycle in this top NV graph. That will give me a sink and I can continue.
So just one quick clarification.
Please, yes.
So related to the normal goods, so there we had only one cycle at a time, or so multiple cycles are possible. There it's okay if you break even not the best one.
Yes. Yes.
But here exactly it creates a problem. Okay.
Exactly right. Exactly right.
Yeah. But it's strange, because it's very symmetric in a sense. And
yeah, absolutely. There were 3 or 4 papers which kind of said, oh, this is so natural, this must hold. And it doesn't.
So one clarification regarding the discussion just had. So suppose in normal good case, one agent could be part of 2 such cycles, right?
Sure. Yeah.
Then which good to swap?
In the goods case, it doesn't matter.
Okay. Anyone?
In fact, it could be that you resolve a cycle and you still don't have a source in the graph. Okay. So then you may have to resolve another cycle. But but every time you do this, you will make some progress and eventually you will have a source in your graph.
Okay.
But it doesn't matter which cycle. For the goods case, it doesn't matter which cycle you resolve.
Thank you.
Okay. Right. Right. So, but with this slight modification, this works. In fact, you can show that for chores, again, your valuations can be pretty much arbitrary. The allocation obtained by this algorithm is EF1.
Just one more thing for the chores. So one can define the max Nash for the chore also, right? In a sense, similarly, like where you minimize maybe the negative product or something like that. I'm not sure.
It doesn't have any nice properties.
Okay, so the implication of the normal good is that max Nash imply EF1, and that will not hold here, right?
That will not hold for. I mean, we tried this a lot, in fact, but any natural definition of Nash versus welfare for chores will not give you any nice properties. Okay, right. So so I'll stop here. I'm just going to do a recap quickly. I think I'm almost at the end of time as well. So maybe I'll just skip the recap. We know. I'll just quickly go ahead. In fact, I want to spend a few minutes with the open questions. So the open questions, firstly, as we said in goods, we can find an EF1 plus few in pseudo polytime, and we do this in polytime. I mean, and you might wonder why do we care? It's a very theoretical, technical question, one that has been bugging me in particular. Anyway, we said that the optimal Nash welfare we can't really obtain in polytime. Well, what is the best you can do? How close can you get to the optimal Nash welfare? So this is an open question as well. And for chores, well, we know how to get an EF1 allocation. We don't know if an EF1 plus PO allocation exists. And so we know how to, I mean, like, again, as was mentioned, so for goods, we know that NSW, the optimal Nash welfare gives us EF1 plus PO, but we don't know of any corresponding result for chores. And in fact, if you start combining goods and chores, then we don't even know if an EF1 allocation exists, right? So yeah, and there's a whole ton of open questions. I'm just mentioning maybe 4 interesting ones. I'll stop here. There's a whole bunch of things which people are interested in, which I didn't cover. Just to mention, so I talked about proportionality and NV freeness. There are a whole bunch of other fairness considerations, including equitability, EFX, max min share. For the cake setting corresponding to chores, there is something called burnt cake, where you have a negative, a negative density function for the cake. You could talk about strategic agents, right? I mean, you may ask, well, is it in the agent's best interest to reveal her value for the various items? Right? And can you come up with strategic proof algorithms? We talked about approximation algorithms for max Nash welfare. Well, we didn't talk about approximation algorithms for max Nash welfare. Price of fairness, rather than individual fairness, we can also ask questions about group fairness. Yeah. But I'll stop here. I think I'm out of time. Thank you.
Okay, so thanks. Yeah,
Louis, go ahead. Go ahead.
Okay.
I just want to ask 2 doubts if
yeah, sure. Go ahead,
yeah,
Sarvesh.
yeah. So Umang, in your open question, the last one you said for the arbitrary objects. So by arbitrary, you mean like infinite? That's what you mean, or?
No, I was actually talking about the finite item indivisible case. So you're talking about, go on.
So, but you so what was the open question for the arbitrary item?
So the problem more precisely is the following. So supposing you have a cake, right? So a cake has like supposing an item can be a good or a chore depending on what bundle you already have.
Okay.
So if you have items, so the marginal value is neither fixed to be positive nor negative.
Okay.
In that case, we don't know whether they always exist in EF1 allocation or not.
So by arbitrary, you mean that it could be good or it could be bad?
It could be good or bad. In fact, whether it's good or bad would depend upon what the agent already has. The partial allocation of the agent.
In fact, I'm interested to ask something which you didn't cover, but you are the expert of this area. So actually, sometime back, I read literature on EFX for the NV free for any good. So I found to my understanding by last year, the latest result was that for the 3 agents there exists, right? I think Jugal Garg or some, so they have shown.
Yeah, there is.
So is there any progress after that? Because I got very curious and no. Okay.
No, unfortunately not.
Oh,
unfortunately, some special cases are known if there are identical valuations.
Right.
All agents are identical except one. Those kind of things.
Exactly.
But
so
beyond 3,
even for additive, more than 3 is not known, right?
Just for additive. All of the results.
Just for it. Yeah. Oh, so still it's pending. I thought maybe by a year it will.
No.
So I tried, but it seems a very obvious problem to try. Very interesting. You can make small examples, and I was.
I mean, you could simplify this for yourself. Make a negative answer more likely. You could ask, well, like let's say goods, but sub-additive utilities. Right? Then can you give me a counterexample to show that EFX does not exist?
Right. So
even that we don't know.
Thanks.
Sure.
Okay, so thanks, Umang. for this talk. And so now the floor is open. If there are any more questions, then participants can ask right now. Do we have any more questions?
Or is the director by any chance coming now? No.
He was in the boardroom last I checked. So I have kind of put in a request that he can give an address tomorrow before tomorrow's sessions at 6 tomorrow.
Okay. Okay. That would be great. But then we have to wait till he comes in tomorrow. That's all.
Probably. Yeah.
Take it.
So, okay. So any questions? Yeah. Okay. So if there are no questions, then let's close today's session. Again, thanks a lot, Umang, for this talk. It was very insightful for all of us, and especially for those who have this interest in theory and understanding the examples that you gave about these different applications that already exist. I think those are the kind of applications that I believe we were specifically interested in understanding, and so we really enjoyed the presentation very much. And of course, thanks Saptarshi for the first talk today, and I hope to see everybody here also tomorrow for tomorrow's sessions. So we have lined up 2 very interesting talks on machine learning. So I look forward to seeing all of you. So thanks. I'm saying on behalf of all the participants, all the members of CMC, and happy to have Joydeep joining us from IIT Kanpur, who's currently the coordinator of this center. So thanks to all. And
Oh, is it?
Yeah.
I had no idea I was the coordinator.
Yeah. So, okay. Yeah, I think that was discussed in the last meeting.
Oh, director
You've
was telling her.
forgotten. Yeah. Okay. Good that I reminded you then.
Okay.
So, okay. So have a great evening, all of you. Hope to see you all tomorrow.
Okay.
Thanks very much.
Thank you.
Thanks so much. Thanks for having me.
Thank you.
Thank you.